smaller slit width, because we know that the light has a wavelength of around what? Wavelength of a light, the visible light, goes from 400 nanometer to 700 nanometer, right? So
Yeah.
we need very small, like, the slit in order for the light to diffract. So when you try to squint your eyes, in that case, you can see the diffraction. I mean, if you're watching, let's say, any source of a light, and you try squinting your eyes, like,
Yeah.
in that case, you'll see the diffraction. Okay. Yes, Dipra, did you get this?
Yeah.
Okay. We will see more diffraction through the more number of slits as well. So here, you remember principle of superposition? What is principle of superposition says that?
The result, like the amplitude kind of gets added, like onto this. The waves in
So
opposite direction, like
if we have any two waves, it not needs us to be necessary to be identical. Wave one, and then wave two. All right. Then in that case, if I have to identify the net displacement at any position. So let's say the wave one, this is the horizontal midpoint, this is the horizontal midpoint. If I wanted to find out what will be the resultant wave or the resultant displacement at this particular point, so I'll read the displacement of the wave 2, and I'll read the displacement of the wave 1 at that point. So let's say, for example, if the wave 1 has a displacement of 3 and wave 2 has a displacement of -2, then the resultant displacement will be +3 -2. So that'll be +1 unit. Okay. So the
yeah.
superposition says that the net displacement of the wave 1 is the initial displacement of wave 1 plus the wave 2. Yeah, so y1 plus y2. Got it.
Yeah.
And superposition is applicable for any two wave. For any two wave. It is not necessary to be identical. It's just that how do you add the displacement of the wave? It's not called as amplitude, huh?
Yeah. Displacement.
The displacement, because amplitude is maximum displacement. Okay.
Yeah.
So if I ask you at which point the displacement could go maximum, I mean at which time interval, so I can see if I draw maybe something like over here at this,
Yeah.
because they both are maximums at that point, right?
Yeah.
Could be. So you can figure it out at which point the displacement is going to be maximum by adding them. Okay.
Yeah.
Then you remember the interference. Interference is basically for two identical waves when they're moving in the same phase or out of phase. Okay.
Yeah.
So you have a wave one, and then you have another wave which are in phase. So when I say in phase, that means they have the phase difference of 0 or 2 pi. So at that point, what happened? Let's say at this spot, both the waves are in phase, so they have the same amplitude and same direction as well, right? So the
Yeah.
resultant amplitude will be twice A, correct?
Yeah.
It'll
Yeah.
be 2A. And if I draw the exact same thing over here, but the second one, I'm gonna move it slightly to the left. Let's say this. So now what's gonna happen? This wave has an amplitude of -A, and this has the positive A. So when they join together, the resultant will be simply zero amplitude, right?
Yeah.
So zero amplitude, in the sense, it is called as the destructive interference, and this is what we call it as the constructive interference.
Yeah.
Fair enough.
Yeah.
We will see that how does the path difference affects the constructive and destructive interference. So this is what I'm going to draw, the two source interference. Let's say two source interference. Okay, so let me just draw this. Let's say I'm going to keep a source over here, and I need to draw wave one, 1, then 2, 3. This is 4, and maybe 1, 5. So let's say I drew, this is a source 1. I'll call it as a source 1 at the center. And let's say I have the source 1, and I'm going to do identical, duplicate the source 2 as well.
Yeah.
And they are placed at equidistance, I mean. So check this. Fair?
Yeah.
This looks very messy, but yeah. I mean, you can see there's a source 1, and then the blue color, the red color one is a source 2. That's a 2,
Yeah.
and that's a 1. You will see all these arrows like this. The space between them is the wavelength, right?
Yeah.
And they're identical source. What do you mean by identical source?
The frequency.
The frequency, amplitude, and then wavelength, and then speed, all of them are identical. Okay.
Yeah.
You know, for identical source, we also use a term called as a coherent, source or coherent wave. So coherent source means when the two waves are identical, like frequency, amplitude, wavelength, and speed, and it also means the constant phase difference.
Yeah.
Constant phase difference. So that means the phase difference is not changing. See, phase difference will not change only when the frequency won't change or wavelength won't change. All right.
Yeah.
So you can see now I'm going to take certain numbers over here. Let's say if I take any point, I'll call this point to be P. You see that, right?
Yeah.
So what is this distance from S1 to point P in terms of wavelength and S2 to point P? So I take for point P, for point P, this is called as the path difference, S1P and S2P, right? So as you
Yeah.
can see, each wave is different by lambda only. So S1 to point P is 1 lambda apart, S2 to point P is also 1 lambda apart, correct?
Yeah.
So here we define something called as a path difference. Path difference. So path difference, I'll always take the the mod value of it. This will be S1P minus S2P, the extra path travel. That's called as path difference. So right now,
Yeah.
what's going to happen to the path difference? It'll be 1 lambda minus 1 lambda. So that will be 0 lambda, correct?
Yeah.
So when the path difference will be 0 lambda, that means the waves are meeting like this manner, one over another, that they're superimposing constructively. So the amplitude should add up to 2a, and at that point you will get the constructive interference.
Yeah.
Got it?
Yeah.
Now let's think about this point. If we call that point to be here, what about at this point x? The same way, S1 to point x and S2 to point x, the path
2
difference will be
lambda.
what?
2 lambda minus 2 lambda. So 0 again.
So again 0, right? You will get.
Yeah.
Can you tell me a point where the path difference is gonna be, uh, 1 lambda?
1
So
lambda.
it will be, let's say, here. If I take,
Like up like over there.
if I take this point, let's say that. So what that path difference is gonna be? So from the S1, it'll be 1, 2, 3, and from from red, it will be extra 1, right? So 1, 2, 3,
Yeah.
4, right? So in that case, the
Yeah.
path difference will be 1 lambda.
Yeah.
So here is the general criteria for constructive interference. Constructive interference whenever the path difference, if the path difference come out to be like n lambda, where n could be like the 0, 1, 2, 3, 4, and so on. In that case, you'll get the constructive interference. You will always get the bright spot if it is a light, or you will always get the maximum sound if it is the two sound source, or loud sound, you can also say that. Okay.
Yeah.
Or you get a high voltage or high signal, whatever it is, like the terms which are using. Okay. Got it. That's called as constructive interference. Constructive interference. And then criteria, this is called as a criteria. This is given you in your data booklet.
Okay.
So wherever they'll ask you, explain why that point is like the bright, you will say that because constructive interference is taking place, and you can say that the criteria is whenever the path difference is n lambda, in that point there'll be a constructive. Okay.
Yeah.
Now, how do I write down for destructive interference? Can you spot a point for destructive? So, okay, in this wave, destructive interference where the path difference will be half integral multiple. That means crest of one wave and then trough should be like this. Maximum amplitude and then minimum amplitude, like this. So let me identify one point. So if I take, let's say, sure. If I take a point like this. Correct. So from, let's call this point to be Z, that point Z, how much is distance from S1 to point Z and S2 to point Z?
2 lambda and then like 2.5.
So S1 to point Z
is 2 lambda, 3 lambda, sorry.
3 lambda.
3 lambda.
And S2 to point Z
was 1 to 2.5.
2.5. Correct. So for point Z, can I say S1 to point Z? Okay, S1 is a black one, so it will be complete 3 lambda, as you can see, right? It's like 3 wavelengths apart. So like 1, 2, and then third, like over here. And S2 to point P will be 1, 2, and then it's in middle, right? So that's why it's called as 2.5. That is the point where it's called as destructive interference, right?
Yeah.
So S1 to point Z will be 2.5 lambda. So now in this case, the path difference comes out to be 3 lambda minus 2.5 lambda. So that comes out to be 0.5 lambda, correct? So this 0.5 lambda is also known as 1/2 lambda. So this is where you get the destructive interference. Destructive interference. So for destructive interference, I'll say that the path difference has to be equal to n plus half lambda. This is also known as integral multiple of lambda. Half integral multiple of lambda. Okay?
Yeah.
This is also called as half integral multiple of lambda. So in this case, n could be again 0, 1, 2, 3, so on and so forth. If I put n is equal to 0, so path difference will be half lambda. If I put n is equal to 1, path difference will be 1.5, which is 3/2 lambda, right? And so on. That's what you can see it over here. Set waves. So you can see this two source light, and then on a screen you will see there will be a point or places where the constructive and destructive interference is taking place, right?
Yeah.
So you can see this is the spot, like if I just annotate over here, this is the spot where the path difference comes out to be 0 lambda. All right, because the waves from here and then waves from here, they're meeting constructively. Then you'll reach a point a little distance ahead. At this point, that's a destructive interference. That's the
Yeah.
first, we can also call it as the first minima. So at that point, at the first minima, the path difference comes out to be 0.5 lambda or 1.5 lambda. It'll be 1.5 lambda distance apart. Then you get the first maxima, I mean. So at again the first maxima spot, the path difference will be what? What will be the path difference of first maxima?
The first maxima, like half lambda.
Half lambda more, right?
Maxima, sorry. So that's the maxima is lambda.
Lambda, right? So at this first maxima, path difference has to be 1 lambda. And so on
Yeah.
and so forth. Okay?
Yeah.
So correct. So this will keep, like, for every half integral multiple of lambda, you'll get a destructive. For every integral multiple, you'll get the constructive interference, right?
Yeah. Yeah.
Okay. So we'll see. That's the two source interference. So you'll also see, like, if I draw this directly over here, all these lines will be a maximum bright spot. Then if you see at this spot, all these lines are gonna be dark spot. This dark and then bright, because you can see it's somewhere in the middle.
Yeah.
So as you can see, this spot, like, even over here, over here, over here, over here, they all are the dark spot. You can say these are the bright spot. The path difference has to be 0 lambda at this point, correct?
Yeah.
Same on the other side as well. So there'll be like points where you get the half integral again at this point, and again you'll get the integral multiple like somewhere over here. They'll be exactly touching, I mean. Okay. So
Yeah.
fair enough. So now, instead of taking this two source, what is the advantage of it? I mean, so if I draw the intensity pattern for this two source light, let's say the y-axis is intensity and x-axis is, let's say, maybe a distance or something. Then you will see the intensity will follow like this. Maybe something like this. And it'll be identical on left side as well. But since it is a two source, okay, I'll tell you, if it is a two source, more or less all these intensity gonna be the same.
Yeah.
It won't change much. It will change if you move really, really far away, like, somewhere over here. When you move at this point, exactly at that point, there'll be no, like, the intensity will be smaller. So this is what I have drawn as the in general intensity for the two slit light. So instead of taking the two source light, I will take simply one of the source. Let's say here, this is the light wave, and so over here, as you can see, now the light will pass from the slit 1 and then slit 2. So it will cause a diffraction pattern from both the slits, and then it will also interfere as well. So as you can see, I've just tried to draw these two with just the two different colors, so you can understand that light from the slit 1 and slit 2, they both diffract as well and interfere as well. And if you put it the same light on the screen, then you can see exactly in the middle, like over here, this spot, you will see the maximum bright. This is called as central maxima. Okay, this is called as central maxima.
The spot is like at the intersection of the two, right? Like,
yeah, that's the intersection of the two, or you can also say that's the point where the path difference will be 0 lambda. Okay, the path difference has to be 0 lambda at that point.
Yeah.
Then you'll reach, if you move slightly more, then you will see the first minima, which is also called as the dark fringe. Okay,
Yeah.
dark fringe. So now I'm gonna call it as, I can call it as like, the first dark. Then you will reach another like, distance apart, that's called as first bright. Then again second dark, second bright, and alternatively so on. You will get the same thing on the other side as well. So like one dark, first dark, then one bright, then second dark, and then second bright. Got it?
Yeah.
I can write down that like this is the spot. Central maxima, if I talk about the path difference directly over here, so path difference will be 0 lambda. For first dark, the path difference will be 1 by 2 lambda. For first bright, the path difference will be 1 lambda, 1.5 lambda, 2 lambda, correct? Same
Yeah.
goes over. I can say 1.5 lambda, 1 lambda, 1.5 lambda, and then 2 lambda, right? The path difference spot.
Yeah.
So for central maxima, you will always see the path difference to be 0, and that is the brightest spot. So like in my diagram, that's the intensity will be, okay? First central maxima. Then you can say this is the one dark spot, and this is the first bright, second dark, second bright, third dark, and then third bright. All right. Here we define the terms like the fringe separation. So what is the fringe separation? That's a distance between central maxima to the first bright. This distance is, we call it
Okay.
as the fringe separation.
Okay.
So in your graph, you can also say this is the fringe separation. If the x-axis is the distance, then from central maxima to the first bright, that's also called as fringe separation, which is, by the way, identical even if you take the first minima to the first, like, the next minima.
Yeah. Distance.
Okay, so the fringe separation, they will write it with a letter S. S they have denoted with a fringe separation. So what
Okay.
is the distance between? So I can say the distance between two consecutive maxima or minima, which is nothing but S, and that is called as fringe separation. That's why the maximas and minimas are equidistant apart. So if they ask you what is the distance between maxima and minima, there'll be half of fringe separation, S by 2. All right. That's gonna be half of 2, that's S by 2. Did you understand?
Yeah.
So S by 2 will be the distance between maxima
I mean,
and minima. Yeah, sometimes they may ask you to calculate it as well, right? So you can count it and you can see how many maximas and minimas are there.
yeah.
See, the two maximas makes it one fringe separation. Similarly, the two minima makes it one fringe separation. All right, so you
Got
can
it.
count that value.
Yeah.
So maybe let's say that they have given this entire distance from here to here. Let's say if it is given as 15 centimeter, for example. Okay, so what will be the fringe separation gonna be? So as you
So,
can see now, go ahead.
so it's a distance of two maxima. So 7.5.
7.5. So 7.5 will be the S, right? In that case.
Yeah.
So that you can figure it out. All right. Okay. Then there is a formula, like the relationship between S lambda, capital D, and then small d. I'll tell you what are the each letter stands for. Okay. In the above formula, or above what are the each letter stands for. So here, the distance between the wave fronts. These are the wave fronts, right? Wave fronts. The distance between the two consecutive wave fronts is nothing but the wavelength. That's a light which has been passing through it. This was the slits. So you can see there's a two slit. If I take a half of first slit and half of second slit, then the separation between them is called a slit separation, which is the tiny d. So I'll write down this over here, lambda being the wavelength of light, wavelength of light. The tiny d is called as a slit separation. Okay. So usually you will keep it everything in meter. Slit separation will be also in meter, but you expect this number to be really small, right? Because slit separations are hardly few millimeters or few micrometers. Okay. Then there is this distance which I need to. This is the distance from slit to the screen. This horizontal distance between slit to the screen. This is called as the distance between slit and then screen. So capital D is that.
Okay.
Is the distance between slit and screen. Distance between slit and screen. And obviously I'm going to say also like S being the fringe separation. Fringe separation. Got it?
Yeah.
S will be the fringe separation. All right. Then S will be the fringe separation. So here comes this formula which is given in your data booklet, and that says that the S is equal to lambda capital D upon small d. S is equal to lambda capital D upon small d. Now, so where the S is of nothing but the fringe separation, lambda is the wavelength, capital D is the distance between slit and then screen, and tiny d is the separation between the two slits. Okay. So
Yeah.
you expect this fringe separation is directly proportional to the capital D. If you take the screen further and further away, then you will see the fringes will be more spaced out. When I
Yeah.
say fringes will be spaced out, that means the bright spot will be more further apart, like that. Okay.
Yeah.
Central maxima and then one bright, or the dark spot will be also further out. Then S is inverse proportional to the D. If you reduce the slit separation, then fringe separation will be increased. And also S is directly proportional to the wavelength. Increasing the wavelength increases the fringe separation. Now we know in that white light, the Vibgyor color, okay, the red has the longest wavelength compared to the violet light, which is the shortest wavelength, right?
Yeah.
So whenever the wavelength is shorter, that means the fringes will be smaller, right? I'll show that using the simulation over here. Let's check this. So instead of taking like two source, I'm going to use a slit first. So I'll take, let's say, two slit, as you can see on this. So the light will pass through each of the slit, then each slit causes a diffraction, and then the light will meet as well. So that causes the interference pattern. And if you see the screen, then you can see that's a spot where the maximas and minimas are formed. Okay.
Yeah.
So right now they have used it for the green light, and as you can see, how I'm gonna measure this, like the fringe separation. So if I take, let's say just for here, half of the central bright to the next consecutive bright, whatever this number is, I'm not counting it. I'm just gonna prove that it's for green light. This is the number of this is the slits, like fringe separation. If I
Yeah.
keep it for red light, everything else the same. I'm not changing anything else, just for the red light. And look at the fringe separation. It won't be the same. It has to be higher. So right now you can see, right? The fringes are
Yeah.
getting smaller in this case, right? The fringe separation has increased because its a wavelength will be longer, right? Then I can also prove that if you increase or if you decrease the, like, so right now this is the fringe separation. Now I can change the screen. See, I can keep the screen, the distance between slit and the screen smaller or larger, right? Like this. So if I
Yeah.
move it to the left, the distance is maximum. And in that case, the fringes will be further spaced out. As you can see now, right? If I keep it closer to the screen, the distance has been smaller, the fringes will be small.
Yeah.
Correct? So that way. You can also increase the slit separation, I mean. So right now, I'm gonna change the slit separation. So if I reduce the slit separation, as you can see, the tiny d has been reduced. And if the tiny d has been reduced, the slit fringes will be further spaced out again.
Hmm.
Okay?
Yeah.
Makes sense? So these are the formulas which you need to understand. This formula is given in your data booklet. So this is how you calculate the fringe separation. All right?
Yeah.
Okay. Uh, here is this. If I draw this intensity versus distance, then central one will be maximum bright. Central fringe will be maximum bright. It'll be identical on either side, and then it'll be like this, and then it's getting smaller and smaller. The intensity is reduced, smaller and smaller. No, why? I mean, why the intensity is reduced over here when you go further away from the screen? When you go in this way further away from the screen, or like this way further away from the screen, why the intensity has been reducing? Yes, Vipra.
Yeah.
So why the intensity of the second maxima is smaller compared to the first maxima, and similarly the third maxima is even smaller, fourth maxima is also getting smaller. So one reason you can see, the intensity is also proportional to inverse of the distance square. Remember, the when you take a candle, let's say that, and if you try to measure a distance, intensity at this point, and if you take the same intensity at this point, when you further apart, then intensity is inverse proportional to the square of the distance. Do you remember this formula? No?
From?
No?
No.
No? Okay, let me show you what it is. So the first, this intensity and energy thing, intensity and energy. So we said the energy of a wave is proportional to the amplitude square, right? It's
Yeah.
also simple harmonic motion, I mean, correct?
Yeah.
The amplitude square. On correct. So intensity is proportional to the amplitude square. So when the waves will be added up, like let's say the amplitude A and then amplitude A, at that point the amplitude becomes 2A. So something like each amplitude has an intensity or energy, let's say E, then this becomes 4E square, right? Or 4E.
Yeah.
Because that's been double and then square.
Square. Yeah.
So we can also check this if there's a candle and that is delivering the power, let's say the P. And if I wish to find its intensity at a distance x over here, but the candle will be delivering its power in all three-dimensional, right?
Oh yeah, I
It's
remember
a kind
this.
of sphere, right?
Yeah, yeah, yeah.
So in that case, the area of the sphere of a radius x, so intensity is actually power spread per unit area, or like surface area. So surface area in this case will
Yeah.
be 4 pi x squared, right?
Yeah.
That's why we say intensity is inverse proportional to the 1 upon x square or d square.
Hmm. Got it. Yeah.
All right. So,
Yeah.
so if you move further and further away, like let's say at this distance, the intensity is even smaller, right?
Yeah.
So in the double slit experiment, the central one is like the vertical, or you can say the perpendicular distance, right? You can say that.
Yeah.
But
And
as you
then the
move like this distance
increase.
will be slightly more. This distance
Yeah.
will be even more, and this distance will be even more, right? So when you
Yeah.
go further and further away, the distance has been increased, And that's the reason, like, the intensity will be getting smaller and smaller. Okay.
Yeah.
So this is the ideal, like, the the two slit. We can also say uh, the two slit of negligible, non-negligible width. She called it as non-negligible width. Okay. But if I make the slit width really, really tiny, so think about this. What I'm saying, the width now. Actually, I'm talking about this separation. So this is called a slit width.
Yeah.
Slit width. So if I decrease this slit width to really small, so if I decrease the slit width to really small, the wave will spread like this manner now. Okay, it'll spread like this manner. Like it can spread in this direction as well. All right.
Yeah.
So in that case, the light from both the slit will spread more, and then they reach the intensity more. Then you can see in this scenario, the intensity of a light will be very much same as, like, the central intensity. So this will be considered as non-negligible slit width. Means non-negligible slit width means when the width of each slit is really small, the light will spread more in all direction, and at least first few maxima is gonna be equal intense. So this
Yeah.
is the the characteristic of negligible slit width. My bad. Negligible slit width. If the slit width is negligible, all these maxima is gonna be equal intense apart, right?
Yeah.
Did you understand this?
Yeah.
Okay, so let's do a little question. Hmm. Open from your. This is what I've explained you, right? The diagram. The
Yeah.
path difference will be 0 lambda, 1 lambda, and then 2 lambda. You get the constructive or destructive interference. And
Yeah.
you can see it over here. The constructive interference occurs when the path difference has to be n lambda. Destructive interference, half integral multiple of lambda, right?
Yeah.
Oh, okay. So we're gonna paste this question. Place it over here. And we also do. So yeah, also you can see this is the formula which will be given in your data booklet. All right.
Yeah.
Now you can see these two, example, like the graph. Look at the graph of this intensity versus the distance. So now the central, the maxima has an intensity of 4 in some arbitrary unit. The first maxima has an intensity of also 4. Second is also 4, right?
Yeah.
What will be the distance between central maxima to the first maxima will represent?
In the center, this is the fringe difference.
Fringe difference, which is also called as fringe separation,
Yes.
right? Yeah. Now, how does these two graphs are different? So you can see now intensity has been reduced a little, right?
Yeah.
So the intensity pattern for the two slit, first one is negligible width. In case of negligible width, all of the intensity is the same.
Yeah.
Okay, this is what the negligible width is. all of them same intensity. In second one, a width with the non-negligible. So in that case, there is this intensity is reducing. I mean, a little. Okay.
Yeah.
And horizontal distance is labeled by this letter Y. All right. So over here, I'm gonna give you this question as well. Copy, and then let's look at this. All right. So let's try these two questions. You first try it by yourself, and then we'll come back. We'll discuss the answer. All right.
Yeah, done.
Okay. So first one, what did you get? There'll
So
be
you get
construction.
it's destructive when you get the path difference is minus 4.5.
Because you can see no path difference. Yeah, path difference is
12.
16.5 minus 12, which is 4.5, right? Is it integral or half integral? So
Yeah.
you can say it's a 3 meter, right?
Yeah.
So can I also say 16.5? If the length is 16.5 meter, how many waves it will fit on it?
So
Of each
15
of
and a
length
half.
3.
So
16
five and a
point.
half.
Go ahead. 5.5.
Yeah.
5.5. And this is 3, right?
Yeah.
So 5.5 lambda minus 3 lambda, that will give you
2.
2.5 lambda, right? So now I
Yeah.
can see the path difference will be, it is fitting n plus half lambda category. That's why it will be a destructive interference. Okay?
Yeah.
And at that point, the intensity will be 0. True. How about this? Question 4.15.
Yeah, so your lambda is easy to calculate. You get S is equal to 0.5 10 raised to
S is equal to 0.5
into 10
into
raised to
10
minus.
raised to minus 2 meter. True.
And your other data is all given in the question.
The
So
wavelength has been given as no, the
no,
wavelength is
in
not
the
been given.
finding, that's your D is given. Capital D is 3.8.
And then capital D is 3.8. Yeah.
You can calculate lambda. You get it as 5 into 10 raised to minus 7.
So lambda will get 5 into 10 raised to minus 7.
5.5.
5.5. That's fine. Okay. Suggest the effect on the separation of fringes by decreasing the wavelength.
If you decrease wavelength, the separation decreases by the formula.
Because yeah, so S decreases, wavelength decreases, right? Okay,
Yeah.
state the feature of the graph that enables you to decide the slit width is negligible.
The intensity is remaining at 4.
Intensity is uniform or like maximum, right? Throughout.
Yeah.
Okay. Now you expect this. How does the fringes are formed? So you can see the same example. Like now, fringes will be formed like this, correct? Passing the through slit through this. Let me tell you. So if I pick this, sorry. Let's say now this medium, which is over here, this medium, which was air earlier, right?
Yeah.
Sorry, not this medium. Let's say over here, this was the lambda. And now I replace that medium air with the water. So now this is water.
Yeah.
What will be the effect on the fringes gonna be now? If air is replaced
By
with
water.
water,
So lambda.
its effect on
So
fringes.
the speed decreases from air to water. And if your
You said
speed decreases, that means your frequency is your wavelength will decrease, right? Your speed decrease.
because frequency never changes,
It doesn't change.
so
So,
your wavelength reduces. True.
then your S is equal to D lambda. So then S will also decrease.
So S will also decrease. Correct. You understood?
Yeah.
So yeah, so that's it for like in this. We will do the single slit diffraction and multiple slit interference maybe in the next class. That's the grating thing. All right.
Yeah.
Okay. I'll send you some homework which you can do that. All right. I'm sending you some questions. All right.
Cool.
That's it. See you. Bye.
Bye. Thank you.
Welcome.